Anyways, I want to talk about Rolle's theorem and the mean value theorem. And I want to write down the conditions. So when you look at Rolle's theorem, there's a mean value theorem. They both have certain conditions that are in common. So the first condition we have is that f is continuous on the closed interval AB. And the second condition we have is that f is differentiable on the open interval AB. And this appears in both theorems. So I could take this guy, I could copy it, I could paste it here. Both theorems have that. Now, the mean value theorem, the Rolle's theorem has one extra condition. And that extra condition is that when you evaluate the function at the endpoints, you get the same number. So if I were to draw a picture to describe the situation down below, for Rolle's theorem, we need f of A and f of B to be equal. So when I put those y values like that, we get something that looks like this, okay? And then I can just draw a continuous differentiable curve in between. So just so that we're sure that we're talking about the same thing, if I drew my curve like this, does this satisfy the conditions of Rolle's theorem? Yes or no?
Yes.
No. The reason why no, Reagan, is because there's a corner here. When you have a corner, it's not differentiable. Does that make sense? I tried to make it a corner. Maybe it doesn't look like a corner to you, but. So we need it to be smooth. Smooth means no corners, no discontinuities, and no vertical tangent lines. Okay. So instead of doing that, I'm going to make it try to look smoother like this. Now the mean value theorem doesn't look the same way because it doesn't have this third restriction here. So maybe we could put our f of A over here. Maybe we could put our f of B over here. And then the two endpoints don't look the same. They look like this. So let me draw a curve here. So maybe this curve looks like this. Like that. Okay. Now, let's talk about the conclusion of each of the theorems. The conclusion for the mean value theorem is there exists a C in your interval AB such that f prime of C is equal to f of B minus f of A over B minus A. And this thing on the left, this is the slope of the tangent line. And this thing on the right is the slope of the secant line. Okay. So when I go to draw a picture of what this situation looks like this. I can draw a dotted line connecting the two endpoints like this. And this right here, this is the slope of the secant line. That red dotted line there. So what does the theorem say? The theorem says, you know what? There's some point within the interval AB that has a matching slope. So if I eyeball it, it looks like this point right there is going to be my C. So let me label it. At this point, if I calculate the slope of the tangent line, that's parallel to the slope of the secant line. In other words, they have the same slope. So that's what the mean value theorem tells you. Okay. If I were to take this and copy this sentence over, this conclusion over like this. Oops, it's too big, like this, I guess. Well, this is true because Rolle's theorem is really a special case of the mean value theorem. So what's the extra, why is it a special case? We have this extra condition. In other words, f of A is equal to f of B. But if f of A is equal to f of B, what does the numerator up here become? What do you think this becomes, Reagan? If f of A is equal to f of B, this numerator here is?
0.
Correct, right? So 0 over any number is 0. So then we just come over here, we erase this guy, and we say, you know what? When you have that extra condition, that's equal to 0. So that's it. That's why I keep saying Rolle's theorem is a special case of the mean value theorem. Now, if we drew a picture, our picture looks something like this. And I described this to you on Monday. This is the slope of the secant line. That slope is 0. And there's some point in between where the tangent line is also 0. That's not a great drawing, but you get the idea. Okay.